Current methods for understanding how language relates to dynamic 3D scenes evolving over time, what we call 4D language grounding, often rely on techniques like scene-specific Gaussian splatting. While effective, these methods require optimizing the scene representation per scene. This leads to poor generalization. The model struggles with new, unseen environments, and limits scalability, as you need to retrain for every new scene. The core insight of 4DLangVGGT is to move away from scene-specific optimization by creating a model that can learn the relationships between language, 3D geometry, and time jointly. Instead of representing scenes with methods like Gaussian splatting that require scene-specific fitting, 4DLangVGGT aims to learn a generalizable representation of dynamic 3D scenes and then align that representation with language descriptions. This means the model can be trained once on many scenes and then applied to new scenes without retraining. 4DLangVGGT achieves this through two main components, the 4D Visual Geometry Transformer, or StreamVGGT, and the Semantic Bridging Decoder, or SBD. StreamVGGT takes a sequence of 3D point clouds over time, the 4D visual geometry, and uses a transformer architecture to extract spatiotemporal features. It learns to represent the scene's structure and dynamics. The SBD then takes these geometry-aware features and projects them into a semantic space that is aligned with language embeddings. The SBD essentially bridges the gap between the raw geometric data and the high-level semantic concepts expressed in the language description. Let's focus on StreamVGGT. Imagine you have a video represented as a series of point clouds. StreamVGGT processes these point clouds not just individually, but as a sequence. This allows it to capture how objects move and interact over time. It uses self-attention to understand the relationships between points in the scene, both spatially within a single frame and temporally across different frames. This 4D processing is crucial for understanding dynamic scenes. The Semantic Bridging Decoder takes the output of StreamVGGT, the spatiotemporal geometry features, and transforms it into a representation that directly relates to the input language description. The SBD uses a learned mapping to project the geometry-aware features into a semantic embedding space where they can be compared to language embeddings. This allows the model to understand which parts of the scene the language is referring to. The results show that 4DLangVGGT achieves state-of-the-art performance on 4D language grounding tasks. Critically, it performs well even when trained on multiple scenes, demonstrating its ability to generalize to new environments without scene-specific optimization. This represents a significant step towards building more robust and scalable AI systems that can understand the world around us in a dynamic and language-rich way. The gains, up to 2% under per scene training and 1% under multi-scene training, show that it's better than current approaches.